In this example, we will anti-differentiate the rational function x cubed divided by x squared plus 4x plus 3. Now, the key observation is that it is a degree 3 divided by a degree 2. So it is what we would call an improper rational function. This requires the first step to be a polynomial long division so that we can rewrite it in a manner that's more convenient for us to handle. So we need to take x squared plus 4x plus 3 and divide it into x cubed. So we ask ourselves, x squared multiplied by what gives us x cubed? And the answer is x. So we subtract away x multiplied by that function x squared plus 4x plus 3. So we're subtracting away x cubed plus 4x squared plus 3x. When we do so, we're left with minus 4x squared minus 3x. And we play the same game again. We ask x squared multiplied by what will give us minus 4x squared. And the answer is minus 4. So we subtract away minus 4 multiplied by the function x squared plus 4x plus 3. So minus 4x squared minus 16x minus 12. And now when we subtract away, we're going to have minus 3x plus 16x to give us a 13x, and minus a minus 12 to give us a plus 12. And now we need to remember, what this is actually telling us. It's telling us that in order to get the x cubed term, we get this by multiplying together x squared plus 4x plus 3 times x minus 4, and then adding on the remainder term, 13x plus 12. Now, remembering what we want to actually anti-differentiate, x cubed divided by x squared plus 4x plus 3. We can get that function on the left if we divide everything by the x squared plus 4x plus 3 term. So x cubed over x squared plus 4x plus 3 is equal to x minus 4 plus 13x plus 12 divided by x squared plus 4x plus 3. And this is exactly what we were going for. We have now expressed the function that we want to integrate in terms of a polynomial plus now a proper rational function. So if we can perform the partial fraction decomposition on the proper rational function, we will be ready to integrate. So writing down the form of that partial fraction decomposition, 13x plus 12, in that denominator, x squared plus 4x plus 3 is x plus 1 times x plus 3. So two linear terms, so the PFD will be a over x plus 1 plus b over x plus 3. Now, in order to solve for these unknown constants a and b, the easiest thing to do is to take the denominator on the left and multiply both sides by it. And this very nicely clears fractions for us. 13x plus 12 is equal to a times x plus 3, because the x plus 1 terms will cancel, plus b times x plus 1, because the x plus 3 terms will cancel. And now, corresponding to an intelligent choice of x, we can hopefully solve for the corresponding constants. Now, looking at the x plus 1 term with the b, we see that an intelligent choice for x would be minus 1. So if we let x be equal to minus 1, what we have on the left-hand side is going to be the number minus 1 equals a times 2, so that a is equal to minus 2. Minus 1/2. In order to isolate and solve for the b term, we note that we can plug in a equals minus 3. X equals minus 3. So if x is equal to minus 3, what we have on the left is going to be minus 27. And on the right, we're going to have b times minus 2. So b is the number 27/2. So let's put this all together. So recalling what we had on the previous slide, the function that we would like to anti-differentiate is equal to, after our polynomial long division, x minus 4 plus 13x plus 12 divided by x plus 1 times x plus 3. And then, using our partial fraction decomposition, this second part of the integrand can be written as minus 1/2 over x plus 1 plus 27/2 over x plus 3. And at this point, we've really done the majority of the hard work. And the reason I say that is, now that we have it expressed in this simpler form, the 4 antiderivatives we're going to need to evaluate are very straightforward. So 1/2 x squared minus 4x minus 1/2 natural log absolute value x plus 1, just going term by term, plus 27/2 natural log absolute value x plus 3. And it's an indefinite integral, so we have our plus c to go along with it. So kind of the big overall reminders is if it is a improper rational function, your first step needs to be a polynomial long division to rewrite it. Then we find that partial fraction decomposition and then put everything together and evaluate these simpler, easier to evaluate integrals.